আমার প্রিয় শিক্ষার্থীবৃন্দ, সহকর্মীবৃন্দ এবং যে সকল দর্শক এই মুহূর্তে ফেসবুক লাইভ এবং ইউটিউব লাইভের মাধ্যমে আমাদের এই প্রোগ্রামটি দেখছেন, আপনাদের সকলকে আমাদের ফেসবুক পেজ এবং ইউটিউব চ্যানেলে স্বাগতম। আশা করি সকলে ভালো আছেন এবং সুস্থ আছেন। শুভ সন্ধ্যা সবাইকে। আমরা একটা ক্রান্তিকাল পার করছি। আমরা বিশ্ব করোনা মহামারীর সময় আমরা বসবাস করছি। আমাদের শিক্ষা প্রতিষ্ঠানগুলো বন্ধ থাকার কারণে আমাদেরকে অনলাইন ভিত্তিক কার্যক্রম চালিয়ে যেতে হচ্ছে। আপনারা ইতিমধ্যে অবগত হয়েছেন যে পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ের পদার্থবিজ্ঞান বিভাগ আমরা অনলাইন ভিত্তিক বিভিন্ন কার্যক্রম হাতে নিয়েছি ছাত্রছাত্রীদেরকে পড়াশোনার মধ্যে ধরে রাখার জন্য। আমরা ইতিমধ্যে আপনারা জেনেছেন যে ৮২টা ওয়েবিনার, ইন্টারন্যাশনাল ওয়েবিনার, ফিজিক্স ওয়েবিনার সম্পন্ন করেছি এবং আজকে এটা আমাদের ৮৩তম ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনার এবং এই যাত্রায় যারা আমাকে সহযোগিতা করে যাচ্ছেন তাদের প্রতি আমার কৃতজ্ঞতা এবং ধন্যবাদ জানাচ্ছি। আজকের ওয়েবিনারে আমাদের মাঝে যাকে আমরা পেয়েছি, আমাদের আজকের স্যার এবং স্পিকার যে স্যার ডক্টর ইন্দ্র দাশগুপ্ত স্যার এখন কর্মরত আছেন সিনিয়র প্রফেসর, স্কুল অফ ফিজিক্যাল সায়েন্স, ইন্ডিয়ান অ্যাসোসিয়েশন ফর কাল্টিভেশন সায়েন্স, যাদবপুর, কলকাতা, ইন্ডিয়া। স্যার ইতিমধ্যে আমাদের মাঝে সংযুক্ত হয়েছেন, স্যারকে আমি স্বাগতম জানাচ্ছি। নমস্কার স্যার, শুভ সন্ধ্যা এবং আপনাকে অনলাইনের মাধ্যমে আমাদের ওয়েবিনার স্বাগতম এবং আমাদের বিশ্ববিদ্যালয় তথা বাংলাদেশে স্বাগতম স্যার। এবং আপনাকে ধন্যবাদ, আপনি ব্যস্ততার মধ্যেও আমাদের ইনভাইটেশনটা অ্যাকসেপ্ট করেছেন, তার জন্য আমরা স্যার অনেক কৃতজ্ঞ আপনার প্রতি। আপনারা হয়তো ইতিমধ্যে অবগত হয়েছেন যে আজকে আমাদের যে ওয়েবিনার তার টাইটেলটা হলো দ্য ফ্যাসিনেটিং ওয়ার্ল্ড অফ কোয়ান্টাম ম্যাটেরিয়ালস এবং আমাদের স্পিকার ডক্টর ইন্দ্র দাশগুপ্ত স্যার এখন কর্মরত আছে সিনিয়র প্রফেসর, স্কুল অফ ফিজিক্যাল সায়েন্সেস, ইন্ডিয়ান অ্যাসোসিয়েশন ফর কাল্টিভেশন সায়েন্স, যাদবপুর, কলকাতা। আমরা যদি দেখি যে ডক্টর ইন্দ্রজিৎ স্যার এখন সিনিয়র প্রফেসর হিসেবে কর্মরত এবং ডিন একাডেমিক PhD at Indian Association for Cultivation Science and Science, Kolkata, India. He's a recipient of MRSI medal, and he was formerly professor in the Department of Physics at IIT Bombay and IIT Kharagpur. He held visiting professor at Uppsala University Paris, South University of Missouri, Columbia, Max Planck Institute of Stuttgart, and ICTP TST. He is currently the Indian member of the Council of Asia Pacific Center for Theoretical Physics, APCT. আমরা যদি স্যারের রিসার্চ ইন্টারেস্ট দেখি এবং দেখি যে spintronics and Rashba system, spin orbit coupling in strongly correlated system, quantum magnetism and spin liquids, magnetism at nanoscale, disorder system। এবং আমরা যদি স্যারের গুগল স্কোর আইডি দেখি, স্যারের সাইটেশন নাম্বার 2977। সবাইকে ধন্যবাদ। আমরা এখন স্যারের কাছে চলে যাব। স্যারকে আবার আমাদের ওয়েবিনারে স্বাগতম স্যার, আপনি স্যার শুরু করতে পারেন এবং অনেক অনেক ধন্যবাদ আপনাকে স্যার আমাদের ইনভাইটেশনটা অ্যাকসেপ্ট করার জন্য।
আমি প্রথমে ধন্যবাদ জানাবো আপনাকে, প্রফেসর প্রীতম কুমার দাসকে, আমাকে এই সুযোগটি করে দেওয়ার জন্য পাবনা বিশ্ববিদ্যালয় পদার্থবিদ্যা বিভাগে টক দেওয়ার জন্য। আপনি আমাকে বলেছেন যে মূলত বিএসসি ছাত্রছাত্রী এবং অন্যরাও থাকবে, কিন্তু মূলত বিএসসি এই কলোকিয়াম বা এই ওয়েবিনারটা অ্যারেঞ্জ করা হয়েছে মূলত বিএসসি ছাত্রছাত্রীদের জন্য। তো আমি চেষ্টা করেছি সেভাবেই এটাকে যতটা এলিমেন্টারি রেখে বলা যায় সেভাবে বলার। সেই জন্য আমি ক্ষমা প্রার্থী যারা যদি কোনো এক্সপার্ট এই কলোকিয়ামটা শোনেন তাদের কাছে, কারণ এটা খুব বেসিক জিনিস এবং বেসিক উদ্দেশ্যটা হচ্ছে ছাত্রছাত্রীদের এই বিষয়টাকে নিয়ে একটু মোটিভেট করা, যাতে তারা ভবিষ্যতে যদি গবেষণা করার কথা ভাবেন তাহলে এইটাও একটা দিক, সেই ব্যাপারটা বলা। তো এই কথাটি বলে আমি আমার স্লাইডে চলে যাই এবং আমাকে আশা করি দেখা যাচ্ছে, তাই তো?
জি স্যার, দেখা যাচ্ছে।
আচ্ছা, আমি অবশ্যই মাঝে মাঝে বাংলা বলবো, কিন্তু আমার এই উপস্থাপনাটা প্রাইমারিলি ইংরেজিতে হবে, তাই আর এবার বাংলা থেকে আমি ইংরেজিতে চলে আসছি। So what we are going to talk about today is the fascinating world of quantum materials. So as I progress, I will tell you what do we really mean by quantum materials. As Professor Pretam Kumar Das told that I am presently working in Indian Association for the Cultivation of Science. I'll spend a couple of minutes telling you that Indian Association for Cultivation of Science is possibly one of the oldest research institute in Asia, and of course, definitely in this part of the world, particularly Southeast Asia. And this is the institute which produced the only Nobel laureate in physics from this part of the world, right? So you know the C.V. Raman. C.V. Raman essentially discovered his Raman effect from this institute, and this was discovered when India was not divided, right? All the three countries, India, Bangladesh, Pakistan, belong to the same country, and this Nobel Prize winning work was discovered from this institute. So what I would like to say that this institute has a kind of a great legacy, and it still continues to take it forward. Well, with this brief description, let me come to the main theme of the talk. So when we talk about physics, right? When we talk about physics, one of the ways to distinguish between various branches of physics is to look at different length scales. Right? So when we are at a very large length scale, right, like say, some 10 to the power 20 meters or so on, right? So this is what is known as this astrophysical length scale, and that's where our galaxy, universe, star, and so on lives. And this is a scale where, for example, if you want to describe things out there, then Newtonian mechanics or classical mechanics is something which is, of course, works out perfectly fine. There is, of course, another length scale which is less than 10 to the power minus 15 meter, right? And this is the length scale where we are essentially start probing. We start probing inside the nucleus, right, and the elementary particles. And this is where the energy is very high. And this is the range for high energy physics or elementary particle physics. But there is also a length scale, right, which is something between 1/10 of a nanometer to few millimeter. And this is the length scale on which we'll confine our discussion today, right, where one can essentially use either, depending on the length scale, either classical physics or quantum physics, right? So this is the length scale, right, where we essentially see things that we essentially go ahead and apply. Like, for example, the mobile phone that we use, right, and which is very common, the computer that we use, which is very common, right? If you want to understand what makes them work, it essentially falls in this length scale. So today the talk will confine to this length scale, and so the length scale will be something like 1 nanometer, which is equal to 1 into 10 to the power minus 9 meter. And this is the length scale where we'll confine and try to see what we can learn from the length scale. Right. So what I try to convey to you is that very high length scale or very small length scale is something which we're not going to consider. We are going to consider length scale where things which we can see with our own eyes, and we'd like to understand things in much more details in that length scale. Well, let us try to take a look at it in some more details, right? So what we are talking about a material, as I told you, that we are talking about the mobile phone that we use. And you must be knowing that the mobile phone consists of an integrated circuit. And if we go try to probe this integrated circuit, we'll figure out that the material which makes up this integrated circuit is possibly a semiconductor like silicon, and so on and so forth. Right? So typically, for example, if I'm thinking about a piece of silicon in which I'm essentially going to design my integrated circuit, this is a macroscopic continuum, and the typical length scale would be of the order of some microns. Well, so this is the length scale which we essentially can access, we can see with our own eyes, and this is a length scale where experimentalist goes ahead and does his or her experiment. But the goal of today's talk is to understand properties of such materials and to devise methods by which we can essentially go ahead and understand this material, or we can essentially go ahead and predict properties of these materials. Well, how we can go about doing that? That we can take a microscope, and if this microscope is able to probe a length scale between 1 to 100 nanometers, then what we'll figure out? We'll figure out that this material is composed of some atoms, right? And this is what is known as this atomistic scale. Well, which may not be sufficient enough, right? We may also like to know what is happening inside the atoms. And this is what is the electronic length scale, which is less than 1 nanometer. So that is the length scale in which we are going to confine ourselves to understand properties of material is less than 1 nanometer, something between 1/10 of a nanometer to 1 nanometer, or 1 angstrom to a nanometer. And this is a length scale where, for example, we start seeing the electrons, right, and how the electrons behave. And this behavior of electrons is finally going to predict the property of this macroscopic continuum. Well, so if we are interested between macroscopic continuum and atomistic limit, then classical mechanics or the Newtonian mechanics works out. But if you're interested in having a deeper insight, right, and we'd like to probe a length scale, which I told you is less than a nanometer, right, then we have no other option but to go ahead and use quantum mechanics. So this is the length scale that we would be interested in, and to understand properties. And the properties of materials which are governed by quantum mechanics is the simplest way, or the simplest thing that I'll go ahead and call quantum materials. Well, so what kind of questions we can address, right? So for example, you must have seen, right, in some museums or churches, temples or mosques, right, ancient stained glasses, and they give beautiful colors, right? So, and what I'm going to tell you that these are essentially made, that the reason they display such nice colors is because of a quantum mechanical effect. And what is this quantum mechanical effect is something which I'm going to explain you as I move along. Of course, the people who designed such glasses, they never knew about it. They only knew that when you do such kind of things, the glasses can give beautiful colors and beautiful reflection patterns and so on. But when one went ahead and tried to understand the science, then one figured out that essentially quantum mechanics is at work. Well, for example, this giant magnetoresistance which is used in our switches, right, or this concept of a spin valve, right, this also involves quantum mechanics. And I'll also try to tell you how quantum mechanics comes up there, and how and why such a spin valve is useful in our day-to-day devices. For example, the storage in computer that we use, right, is essentially based on a principle of giant magnetoresistance, and which is, in principle is also based on this principle of spin valve. Well, superconductivity is one of the very exciting things, and which quantum mechanics tells us to understand what are high TC cuprates. And in the very recent times, people have been talking about a novel kind of insulators, which are called topological insulators, right, and which is also a kind of a quantum phenomenon. Well, so so what I wanted to tell you is that quantum mechanics becomes inevitable to understand many of the properties which we need to understand in order to design, in order to use, in order to produce many day-to-day life things that we go ahead and use. Right? And this branch of science that I'm talking about is essentially called quantum condensed matter physics, or hard condensed matter physics. Well, this is classical mechanics, and classical mechanics is due to Isaac Newton, and I think all of you are familiar with classical mechanics. And this is a famous problem that you do in your school, that if you throw a ball with some initial velocity making an angle phi, then you all know that it essentially adopts a parabolic trajectory. And how and why it adopts a parabolic trajectory, all of you can work it out. And the basis of this is essentially Newtonian mechanics, where your force is equal to mass into acceleration. So Newtonian mechanics, what it requires, so if you specify the initial position, and if you specify the initial momentum or initial velocity of an object, then you can essentially trace the path of that particle, right? So this is what is Newtonian mechanics, right? So I can always specify the initial position of an object, I can always specify the initial velocity of an object, and then the entire mechanics is deterministic. It is driven by this classical mechanics equation, Newton's second law, force is equal to mass into acceleration. We also know that this Newtonian mechanics holds good, but when the speed of the particle becomes comparable to the speed of the light, then we have to use relativistic mechanics, and this is something which was introduced by Albert Einstein. Well, but there is also a regime, and this is a regime which I was trying to tell you. A regime tar kotha ami bolar chesta korchilam. What is this regime? that if you're in a length scale, right, which is less than 1 nanometer, right, that means 10 to the power minus 9, less than 10 to the power minus 9 meter, right? So then one has no other option, but one has to use quantum mechanics. The reason one has to use quantum mechanics is now I cannot specify precisely both the position and momentum of a particle. And this is due to a celebrated principle called Heisenberg principle. So I have to essentially cannot use this Newton's second law of motion. So I have to do something more, and this is what is was essentially derived by Schrödinger. I have to essentially, to understand the property of particle in this regime, I have to use a new kind of mechanics, which is known as quantum mechanics. And this entire talk will tell you that this quantum mechanics reflects itself in our day-to-day life. When quantum mechanics comes, when the particle size is 10 to the power 9 meter or less than a nanometer, and it moves in with a speed comparable to the speed of a light, then what one uses is known as quantum field theory. But I'll not go to that. But today what we are going to do, today we are going to see how quantum mechanics, that means we are essentially going to look at a length scale, right, which is of the order of 1 nanometer to understand properties of materials. So what is quantum mechanics? So quantum mechanics is a set of laws of nature which are believed to be fundamental, that describe states and motions of fundamental or a small group of fundamental particles of matter and energy, right? So this is what it is. So quantum mechanics is applicable in describing mechanics of constituents of any physical system, since everything is made of fundamental particles, like electron, proton, small group of them and so on, right? Atoms and molecules, right? As I told you that the length scale has to be smaller, and where one has to go ahead and use quantum mechanics, because because of this Heisenberg uncertainty principle, I cannot specify both the momentum and the position accurately or precisely. In fact, this is what I'm going to show you. In fact, many of our day-to-day phenomena require quantum mechanics. For example, why sun shines, this is because of this nuclear fusion. Why there are magnets at finite temperature, you have আপনারা সবাই চুম্বক দেখেছেন, চুম্বক কেন চুম্বকত্ব দেখায়, that also depends on quantum mechanics. And most importantly, how transistors work. The transistor is one of the basic component of an integrated circuit which essentially make our mobile phone computer work, right? এই ট্রানজিস্টরের প্রিন্সিপাল বুঝতে গেলে আমাদের কোয়ান্টাম মেকানিক্স বুঝতে হবে। সো এই যেটা বলার চেষ্টা করছি, কোয়ান্টাম মেকানিক্সের অ্যাপ্লিকেশন টু আন্ডারস্ট্যান্ড ম্যাটেরিয়াল প্রপার্টিস, that is a branch of research, and সেই রিসার্চটাকে বলা হয় condensed matter physics, more precisely quantum condensed matter physics or hard condensed matter physics. Well, with this, let us try to take an example. আমি এখন চেষ্টা করব কোয়ান্টাম ক্লাসিক্যাল মেকানিক্স আর কোয়ান্টাম মেকানিক্সের পার্থক্যটা কোথায় হয়। So what we have done, so we have essentially taken a particle in a box. আমরা যেটা করেছি, একটা বাক্স নিয়েছি, and in this box the boundaries, right, goes to infinity. সেটা দেখতে পাচ্ছি যে এমন একটা রয়েছে যে এই বাক্সের মধ্যেখানে পোটেনশিয়ালটা 0 এবং এইখানে পোটেনশিয়ালটা ইনফিনিটি, এখানে পোটেনশিয়ালটা ইনফিনিটি, রাইট, এবং এইখানে পোটেনশিয়ালটা 0। এবং এরকম একটা বক্সের ভেতরে যদি আমি একটা পার্টিকেলকে রাখি, if we put a particle in such a box, তাহলে আমরা জানি পার্টিকেলটা যেটা করবে সেটা হচ্ছে যে কাইনেটিক পোটেনশিয়াল এনার্জি অবশ্যই 0, কাইনেটিক এনার্জি ইজ ইকুয়াল টু 0, so particle will continue to stay there, right? So এখানে, so this is the kind of a very boring situation. The particle is going to stay there. It will always has a 0 momentum, আর এনার্জিটা যদি আমি ক্যালকুলেট করি, এনার্জি will always be equal to 0. এবার আমি যেটা বলার চেষ্টা করছি, পার্টিকেলটা যদি এটা ক্লাসিক্যাল পার্টিকেল না হয়ে এটা কোয়ান্টাম পার্টিকেল হয়, যদি আমি এটা বলের জায়গায় যদি ইলেকট্রনকে রাখি, রাইট, তাহলে কি হবে? তাহলে যেটা করতে হবে আমাকে সেটা হচ্ছে যে আমি আর নিউটনস লস অফ ইকুয়েশন ব্যবহার করতে পারবো না। সো হোয়াট আই হ্যাভ টু গো হেড এন্ড ইউজ, আই হ্যাভ টু গো হেড এন্ড ইউজ Schrödinger's ইকুয়েশন, আর এখানে যেটা করা হয় যেটাকে বলা হয় টাইম ইন্ডিপেন্ডেন্ট Schrödinger ইকুয়েশন। এবং টাইম ইন্ডিপেন্ডেন্ট Schrödinger ইকুয়েশন করলে আমি যেটা বলছি, এই পার্টিকেলের যদি টাইম ইন্ডিপেন্ডেন্ট Schrödinger ইকুয়েশন আমি ব্যবহার করি, তাহলে আমি যেটা পাবো সেটা হচ্ছে পার্টিকেলের এনার্জিগুলো আমি ক্যালকুলেট করতে পারবো, এবং এনার্জিগুলো এক্সপ্রেশন এখন আর 0 হবে না। এনার্জিগুলো দেখা যাবে যে এনার্জিগুলো কিছু ডিসক্রিট ভ্যালু নেয়, রাইট? এনার্জিগুলো এটা হচ্ছে E1, এটা হচ্ছে E2, এটা হচ্ছে E3, এটা হচ্ছে এবং পার্টিকেলের স্টেট, পার্টিকেলের সেটা এই জাতীয় একটা ওয়েভ ফাংশন দিয়ে বোঝানো হয় যে পার্টিকেল একটা গ্রাউন্ড স্টেট থাকে, এবং গ্রাউন্ড স্টেট দেখা যায় যে বক্সের দুটো এন্ডে পার্টিকেলের ওয়েভ ফাংশনটা ভ্যানিশ করে। ফার্স্ট এক্সাইটেড স্টেটে সেখানে যেটা হয় সেটা হচ্ছে যে পার্টিকেলের এখানে ওয়েভ ফাংশনটা ভ্যানিশ করে, এন্ডে ওয়েভ ফাংশনটা ভ্যানিশ করে। অ্যাট দ্য সেম টাইম ইট অলসো পিক আপ আ নোট অ্যাট দ্য মিড পয়েন্ট অফ দ্য বক্স। সো পার্টিকেলের এনার্জি যত বাড়তে থাকে তত বেশি নোট তৈরি হয়, এবং তার একটা ইম্পর্টেন্স যেটা আমরা পরবর্তীকালে বোঝার চেষ্টা করব। তো আমরা যখন কোয়ান্টাম পার্টিকেল এর কথা ভাবছি, তখন কোয়ান্টাম পার্টিকেল হলে পার্টিকেলের এনার্জিটা জিরো নয় ক্লাসিক্যাল পার্টিকেলের মতন, তার অনেক রকমের অনেকগুলো এনার্জি থাকে, এবং সেই এনার্জিগুলো তখন এরকম একটা সংখ্যা EN দিয়ে ডিসক্রিট নাম্বার দিয়ে বোঝানো যায়, এবং করসপন্ডিং টু ইচ এনার্জি পার্টিকেলের অবস্থানটা বোঝানোর জন্য একটা ওয়েভ ফাংশন ব্যবহার করতে হয়। তো এইটা হচ্ছে বেসিক ডিফারেন্স বিটুইন আ ক্লাসিক্যাল মেকানিক্স অ্যান্ড কোয়ান্টাম মেকানিক্স, এবং এই পুরো পার্থক্যটাই আসে বিকজ অফ হাইজেনবার্গস আনসার্টেনটি প্রিন্সিপাল। তো আমরা যদি কম্পেয়ার করি আমরা কি দেখতে পাবো, যে এটা ছিল ক্লাসিক্যাল সিচুয়েশন, এই একটা ক্লাসিক্যাল পার্টিকেল নিয়েছিলাম, তার লোয়েস্ট এনার্জিটা জিরো হয়েছিল। যেই আমি পার্টিকেলটাকে একটা কোয়ান্টাম মেকানিক্যাল পার্টিকেলে নিয়ে গেলাম, তখন পার্টিকেলের অবস্থানটাকে বোঝাতে গেলে একটা প্রবাবিলিস্টিক ইন্টারপ্রিটেশন করতে হয়। আমি তার মধ্যে আজকে আর ঢুকতে চাই না। পার্টিকেলের পজিশনটা, পার্টিকেলটা কোথায় থাকবে, পার্টিকেলটা প্রেসাইজ জায়গায় থাকবে না, পার্টিকেলটা কোথায় থাকবে তাই সাই স্কোয়ারের প্রবাবিলিটিটা, সাই স্কোয়ার ক্যালকুলেটে সেই প্রবাবিলিটি বোঝা যায়। কিন্তু সবচেয়ে ইম্পর্টেন্ট যেটা বোঝার ক্ষেত্রে সেটা হচ্ছে পার্টিকেল এনার্জিটা কিন্তু জিরো নয়। পার্টিকেল এনার্জি তখন হচ্ছে এই h² 8m/L² or h² 8m/L², যেটা এই লেন্থের ওপর ডিপেন্ডেন্ট। তো এইটা করতে গিয়ে আমি দুটো আরেকবার গিয়ে বোঝানোর চেষ্টা করব। সেটা হচ্ছে যে এটা হচ্ছে এই বাক্সটার দৈর্ঘ্য বা উইডথ, এবং আমি দেখতে পাচ্ছি সেটা হচ্ছে এই এনার্জিটা হচ্ছে ইনভার্সলি প্রপোর্শনাল টু পার্টিকেলের দৈর্ঘ্য বা উইডথ, এবং এটাই আমাদের একটা নতুন ফিজিক্স বুঝতে বা দেখতে সাহায্য করবে। তো দেখা যাক কিরকম ভাবে হচ্ছে সেটা। So let us go ahead and try to find out. And for this we are going to go to the world of nanomaterials. So what are nanomaterials? So these materials, unlike bar circuits, have size down to few nanometers. আমি যেটা বলার চেষ্টা করছিলাম, এই সিস্টেমগুলো সাইজ হচ্ছে few nanomaterials, তার মানে হচ্ছে তাদের সাইজ হচ্ছে 10⁻⁹ মিটার। এবং আমি আগেই বলেছি, আমি যখনই এরকম সাইজের একটা মেটেরিয়ালকে নেব, তখনই যেটা হবে সেখানে কোয়ান্টাম এফেক্ট কাজ করবে। এবং এই ন্যানোমেটেরিয়াল ইম্পর্টেন্স আমাদের যিনি প্রথম পয়েন্ট আউট করেছিলেন, উনি হচ্ছেন আর কেউ নন, রিচার্ড ফাইনম্যান, and he is the person who said there is plenty of room at the bottom if we can go ahead and try to understand properties of such things, right? That is going to give us a plethora of interesting properties, and this is what people have realized today. Well, so আমি যেটা করার চেষ্টা করি, যেটা একটু আগে দেখালাম, so we take a simple illustration for a particle in a box. আমি যদি একটা particle in a box নিয়ে of width A, right? Then what is going to happen? Then the energy is inversely proportional to the width of the box, right? Energy is inversely proportional to the width of the box, and I have this discrete set of energy levels, right? This is the ground state, the first excited state, the second excited state, so on and so forth. এবার আমি যদি পার্টিকেলের if I now increase the width of the box, if I now increase the width of the box, what is going to happen? Since En is inversely proportional to A², the separation between these energy levels will decrease, right? So that is precisely what is going to happen. So let us see what I have done. I have increased the width of the box. So now the width of the box has increased. As a consequence, since the energy levels are proportional, inversely proportional to the width of the square of the width of the box, so you can clearly see what is happening, that the difference between the energy levels has decreased, right? And this is the lowest energy level. This is the first excited state. So you can see this difference between these two energy levels essentially decreases. So what I'm able to do, so if I increase the size of the particle, then the energy difference between the ground state and the first excited state decreases, right? And this is a crucial property. So what you can do, you can essentially tailor particles, nanoparticles. So you can see this nanoparticle has a bigger size. As a consequence, since the size is big, so the difference between the ground state and the first excited state, it's much smaller compared to this smaller nanoparticles, right? And this is so what you are able to do. So, and sorry, what you are able to do, you are able to essentially go ahead and tune the so-called band gap of this material by tuning their sizes. If you increase the radius of the particle, as you go on increasing the radius of the particle, you can see that separation between the grounds and the first excited state decreases, and as a consequence, if you now go ahead and study their optical property, for example, this has a larger bandwidth. As a consequence, this guy emits in blue, and this has a smaller bandwidth. As a consequence, this guy emits in red, right? So as a সেটাই দেখা যাচ্ছে এই nanoparticle, right? By tuning their size, you can essentially tune their properties, and this has been experimentally observed. তার মানে একই ন্যানোপার্টিকেল নিয়ে সিম্পলি তার সাইজটাকে টিউন করে আমি নীল আলো পাচ্ছি যখন ব্যান্ডউইথ অনেক লার্জ, আর আমি লাল আলো পাচ্ছি যখন পার্টিকেল সাইজটা বেশি এবং ব্যান্ডউইথটা কম, right? So this you can see that here to essentially tune the property, right? I'm using size, and this property tuning of property because of size is happening because of a quantum effect, and so this is what is known as quantum phenomena in operation. And this is something which was realized long time back. This was I was trying to tell. The nanotechnology is not new. Ancient people knew that gold nanoparticles in glass are reflected in red, right? This is what was known. So what people did, ancient stained glass makers knew that if they put finely ground gold or silver in glass, they would get beautiful colors. And why they were getting beautiful colors? Because sizes were small, and since the sizes were small, so what was happening, right? So the quantum effect was coming into the picture, which of course they did not realize. We realized later on after the discovery of quantum phenomena, and as a consequence, they were giving nice colors. And as you can see, or what I wanted to illustrate, that optical properties changed with nanoscale. Well, so these nanoparticles have other applications, and one of the most important applications is, for example, in harnessing energy, right? And I think many of you must have seen solar panels, right? Or I think this must be very common also in Bangladesh, right? We use to save other natural resources. We would like to harness solar power. That means we'd like to harness sunlight and convert it into electricity. How we can do that? So these are done by solar panels, and solar panels are nothing but a series of metallic plates which face the sun and exploit what is known as photoelectric effect. And one of the materials which essentially make up the solar panels are silicon nanoparticles. So what happens here is you put silicon nanoparticles, right? And the way you tune the size in silicon nanoparticles so that you can essentially harness the sunlight. So sun will liberate electrons, right? And this liberated electrons will generate a photocurrent, and this photocurrent can essentially heat your home, run your lights, and essentially meet your energy requirement. Well, I'll not get into the things. So for example, what is done, again, so nano materials are used in trapping solar energy. So what one does, one essentially tunes size of a nanoparticle so that it can essentially harness the solar energy so that the band gap is equivalent to the wavelength of the solar energy or the solar thing. So what one does, so you essentially, sunlight falls on these nanoparticles, and as a consequence, electrons are liberated, and these electrons are liberated, and these electrons are then trapped into a photocurrent, and this essentially goes ahead and provides you with solar power. So for example, this is precisely what is done, and one of the ways to do it is that you take two nanoparticles. So for example, what we have done, we have taken a nanoparticle which is cadmium sulfide, another nanoparticle is zinc selenide, and what you can go ahead and do, you can go ahead and create an interface, right? So you can see this is the nanoparticle 1 whose ground state and first excited state has this band gap, nanoparticle 2 whose ground state and first excited state has this band gap. Now the effective band gap, that means this is these two levels will essentially serve as the effective band gap, right? So then what happens? So this is what are known as band offsets. I'll not get into that in details. So this is what, so you have semiconductor 1 and semiconductor 2, right? So these are electrons. So now sunlight falls on it. Now if the energy of the sunlight matches this band gap, then these electrons will be liberated, right? So these electrons are liberated. So you have holes here, and of course these electrons will come to this semiconductor. So these are holes, that means empty electrons, and these are electrons. And now these essentially can be separated out, and can be generated into a photocurrent. So you can see that quantum mechanics is at work, right, to serve our energy need. Well, so this is what we talked about. So we talked about individual nanoparticles, right? And as you saw, as you have seen for these individual nanoparticles, right, as we go on decreasing the size, the band gap increases. But for example, silicon is of course not an individual nanoparticle. Silicon is a semiconductor, right? So that, which implies that many silicons essentially form a crystalline silicon. So what happens to the quantum mechanical energy levels in case of a silicon, right? So this is what is shown here, that if you essentially bring in infinite number of atoms, then this energy levels essentially broaden into bands, right? So these are so-called occupied bands, which are so-called valence band, and these are so-called conduction band. And often these valence bands and conduction bands are separated by a gap, and these are called band gap. So, right, and this essentially dictates, right, when a material will be a metal, when a material will be an insulator, and when a material will be a semiconductor, right? And this is something we'd like to understand now, how we can now assemble atoms, right, into solids and go from bonds to bands. So let us try to see this, right? And why they are important, as I was trying to tell you, that for example, we all know that copper is a good conductor, right? So these are these bands, and there is no band gap. On the contrary, a diamond is a good insulator, so it has a huge band gap, and silicon is a semiconductor whose band gap is something like this, which is smaller, usually smaller than an insulator. And for example, conductor, the resistivity increase for a conductor, you can see the resistivity increases with temperature, and for a semiconductor, you can see the resistivity decreases with temperature. And metals are good conductors, and of course, we use semiconductors in our everyday life in device applications. So in order to understand whether a system is a metal, semiconductor, or an insulator, what one has to use band theory. The essential feature of the band theory is that the allowed energy states for electrons are nearly continuous over certain energy ranges called energy bands, with forbidden energy gaps between the bands. Let us try to see how we have. So for example, what I have done, I've taken an atom A and I've taken an atom B, and this is the ground state of atom A, and this is the ground state of atom B, and this is this quantum mechanical wave function. Right? When I bring these two atoms closer, these wave functions will overlap, and these wave functions can overlap by two means. They can essentially add up. This is what we have seen. And when they add up, then we say that it's a bonding state. And when they essentially get subtracted, then we say that an anti-bonding. And you can see the anti-bonding state has a node. And as I pointed out, that as soon as the wave function has a node, its energy will be higher. So when I bring two atoms closer, right? So this was an individual atom. This was another atom. When I brought them closer, they form a bonding state given by this wave function, an anti-bonding state given by this wave function. And now these two electrons can go and occupy the bonding state, and the energy is lowered. And as a consequence, these two atoms will form a molecule. And this is the case where hydrogen essentially forms a hydrogen molecule, because by forming a hydrogen molecule, it can lower its energy. Well, so instead of taking two atoms, I can take n atoms, and this is what is shown here. So for example, I have taken one sodium, I've taken two sodium atoms, it forms a bonding and anti-bonding. I've taken three sodium atom, right? It then forms a bonding, a non-bonding, and an anti-bonding. And in the way, when I go ahead and bring in n sodium atom, then I essentially get a continuous energy levels. This discrete energy levels now becomes continuous. I have a continuous energy levels, right? And then there is no gap between the continuous energy level. As a consequence, sodium happens to be a metal, right? So this is what we know. On the contrary, and this is what, and one of the ways to understand system is a metal or not, one can calculate what is, instead of evaluating the individual energy levels, one can calculate what is known as densities of states. That means you count electronic states per unit energy, per unit dimension of the system. For example, this is the density of states for a metal, right? And this is, so till this point, this is what is known as the Fermi level. The electrons are occupied, and this is empty, right? So electrons can easily transfer from the occupied to the empty states. On the contrary, what you have, on the contrary, for a semiconductor, there is a huge band gap, right? As a consequence, this valence band is completely occupied while the conduction band is empty. So the same thing happens when you consider a magnet, right? For a magnet, what you have to do, you have to distinguish between the upspin and the downspin of an electron. So you can see the upspin is occupied in one way and the downspin is occupied in a different way. And this essentially, this difference in occupancy essentially gives a magnetic moment to a ferromagnet. And there is, of course, a new kind of a material which are known as half metal or half metallic ferromagnet, where you can see the upspin is a conductor, whereas the downspin is a semiconductor, right? So these are known as half metal, that is metallic in one spin channel and conducting in the other spin channel. Well, I'll not get into this. So this entire mechanism of band theory is done by using a methodology called density functional theory, which was devised by Professor Walter Kohn, and for this Walter Kohn got Nobel Prize. But if you go ahead and use, for example, this band theory description, then you can essentially predict that your silicon is a semiconductor, and which is essentially the case. So what I'm trying to tell, that you can use quantum mechanics, do a full-fledged calculation, and predict that silicon is a semiconductor, which eventually agrees with experiment. And you all know that silicon had been the building block for our present-day electronics. Whether you talk about diode, whether you talk about transistor, right? Everything is based on silicon technology, and this is the reason for which William Shockley and then Brattain and Bardeen got their Nobel Prize, right, in 1956 for the discovery of transistor. And I also like to point out that Bardeen essentially got 2 Nobel Prizes. He also got a Nobel Prize in 1972 for discovery of superconductivity, which I'll talk about a little later. Well, so now you can see the evolution of semiconductor industry, right? So this is a computer, right, right, early 70s, and you can see the clock speed of this computer was about 2.25 megahertz, and you can see the size of this computer, right? Now you can see that this is a small handheld computer, right, which has 32, and you can see there has been a huge miniaturization, right? So what people started with vacuum tubes, then of course came transistors, then came integrated circuit, and then this is essentially this highly miniaturized or size choto kora, or to reduce the size, is essentially an effect of evolution of semiconductor industry. But you all know that this evolution of semiconductor industry has its own limitations, and these limitations is essentially spelled by Moore's law, right? So for example, I simply cannot use only the charge degrees of an electrons, right, to go on miniaturization, right, because there's a limitations. So now you can see that you basically need billions of transistors, right? And this is our data only of 2010, right? You need billions of transistors, and this is possible. And as I said, the transistor doubles every 18 months, and this has essentially brought in a limitation of the standard semiconductor industry. So one has to think about new thoughts, and this is what is a new direction of research, which is called spintronics. You all know that electron has a charge, and this charge degree of electron is essentially exploited in the semiconductor industry or in semiconductor. But electron also has a spin, right? And if one can exploit electron spin to essentially for the purpose of communication, right? So then you have this new field which is called spintronics, which is spin-based electronics, exploiting electron spin over and above its charge to carry information. So this is going to give rise to new generation of devices with new functionality. That means the property of this material will now be, we are going to exploit electron spin in designing material or designing properties of a materials. So what spintronic devices are expected to have? They're expected to have significant improvement in terms of size, speed, information density, power consumption, so on and so forth. And there are, of course, major challenges, and this happens to be one of the active areas of research. And some of you, right, may be interested in doing research in spintronics. So once we talk about spin of an electron, that essentially brings us to the world of magnetism, because if spin of an electrons, right, if they arrange themselves in a particular direction, if all the spins are parallel, then we say the material is a ferromagnet. If one spin is parallel, another spin is anti-parallel, then we have an antiferromagnetic arrangement of spin, and there can be a variety of arrangement of spin, right? But today we'll be interested in a very special kind of material where it will be a ferromagnet, but it's a ferromagnet, a very special kind of a ferromagnet whose up spins will be metallic, but down spin will be insulating, right? And this is essentially what is known as the principle of GMR, which I'll tell you in a minute. And this was discovered by Albert Fert and Peter Grunberg, and for which they got, and this essentially revolutionized our storage industry. And for this, they got Nobel Prize in 2007, right? So, for example, spintronics was used, right, for the purpose of storage with the method developed by Fert, a French scientist, Peter Grunberg, a German scientist, and which yielded a Nobel Prize in 2007. Well, so at the heart of spintronics is so-called half metals. So, for example, if you take a normal ferromagnetic metal like an iron, then its upspin channel is metallic and also its downspin channel is metallic, right? The same is true for cobalt. But for example, if you take a half metallic system like chromium oxide, then its upspin channel is metallic, but its downspin channel is insulating, right? So this is what's important. That means the upspin electrons can easily move about. Upspin electrons can easily conduct just like a metal. On the contrary, the downspin electrons will not be able to conduct because they have a huge gap. They cannot conduct. So this idea can be utilized in devising a device, and which is known as a spin valve, or which essentially gives rise to this huge GMR or huge magnetoresistance, and this is something which we are going to understand. So this is a schematic picture of such a spin-based device. So what I have done, so I have essentially taken a half metal out here and another half metal out here, and in between I have an usual metal, right? So you can see this is a half metal. If this is a half metal, its downspin channel in this case is conducting, but upspin channel is insulating. This is a metal or a normal ferromagnetic metal where both upspin and downspin channel are conducting. On the contrary, this other one is again a half metal. So what happens is downspin channel is conducting and its upspin channel is insulating. So what will happen if I provide a bias to this material? Then this downspin electron will merely hop to the downspin channel out here because they are conductor, and this downspin electron can easily hop out here, and as a consequence the downspin electrons merely hops around. So system will have a low resistance, or I can say that this state is an on state. So now what I have done, now I have taken a magnetic field and I flipped the spin out here. So now I say that my upspin electron is conducting, but downspin electron is insulating. So when this is the case, the downspin electron which is conducting here will be able to hop here, but now it cannot hop out here because its downspin channel is insulating. So there is no channel by which it can hop. As a consequence, what is happening? This will give rise to a high resistance. So you can see that simply by applying a magnetic field, I can have a switching effect provided I have a half metal at my disposal. And this is essentially the principle of GMR effect, which was utilized, right, in storage, right? And this was the celebrated discovery of Grunberg and Fert. Well, so what people are these days are doing, they are not only combining ferromagnetic materials, but they are also combining ferromagnetic with ferroelectric materials, which is the field of multiferroics. And there now you can have, I'll not get into details, now you can have essentially 4-state memory processes or 4-state memory. So I talked about 2-state memory element. Now you can start having 4-state memory element. And this is also an area of an active research. Well, from this magnetism, we'll now go to the last part of our talk, where we're essentially going to talk about superconductivity, which is also a manifestation of quantum effect, and which also finds a lot of application, and definitely is going to, and if we can discover a room temperature superconductor, this is going to revolutionize our way of living. So what is superconductivity? Superconducting materials are such materials which doesn't have any resistance, right, or extremely small resistance. So the history goes something like this. In 1895, William Ramsay in England discovered helium, right? And in 1908, Kamerlingh Owens could liquefy helium. And the boiling point of helium turned out to be about 4 Kelvin. You can see the very small temperature. This was done in 1908, right? So now, for example, what was discovered is resistivity at low temperature. So if you take a pure mercury, right, and what pure mercury showed that when you measured resistivity measurements of mercury, it yielded zero resistance, right? So absolutely, and of course your short circuit was assumed, and it showed that when mercury was lowered to 4 Kelvin, right, it doesn't show any resistance, right? If you take any material, you have seen that it follows Ohm's law, it shows resistance. But if you take mercury, cool it below 4 Kelvin, right, it doesn't show any resistance. And as soon as you raise the temperature above 4 Kelvin, and this was essentially done by one of the technicians who fell asleep, and once he fell asleep, the liquid, so what happened is that the helium was vaporized, the temperature went above 4 Kelvin, and as soon as it went above 4 Kelvin, mercury started showing resistance. That means there is a temperature which is close to 4.2 Kelvin, below which mercury doesn't show any resistance, and this is what a superconducting materials is, or superconducting property is expected to have. Well, so as I told you, liquid helium, right? The boiling point is 4.2 Kelvin, and if you take mercury and cool it below 4.2 Kelvin, mercury doesn't exhibit any resistance, and this was the first discovery of superconductivity. And you can clearly see mercury, when it was cooled below 4 Kelvin, right, its resistivity dropped to 0. So the value was at that point of it 10 to the minus ohm, which is extremely so this is what and you can see resistivity below TC is less than 10 to the minus 23 ohm centimeter, which is 10 to the 18 times smaller than that for copper, right? So of course this is, and of course for this discovery, Kamerlingh Owens obtained the Nobel Prize. So why a system superconducts was not known, and as I can say, if you are able to design a superconducting wire, then you can transmit electricity without any loss, right? Because I know that we all know that when electricity passes through a wire, there is this loss which is proportional to I square R. The resistance comes on. This is what the heat which is generated by the. But if the resistance is low, then this heat generation will be extremely low, and you will be having an efficient electrical communication. Well, so one of the things was that, of course, mercury superconducts, but mercury superconducts at a temperature which is extremely small, right? It is 4 Kelvin. So people are looking for materials which would superconduct at higher temperature, and this went on. So, for example, during the period 1911 to 1986, right, you can see close to 70 years, right, the highest TC that could be reached was only 23 Kelvin, and that was this alloy, which is niobium germanate, Nb3Ge. The TC could only go up to 23 Kelvin. Well, so then in 1986, there was a breakthrough, right? So this compound was discovered, which is known as lanthanum cuprate, La2CuO4, and it was discovered by Benrose and Muller in IBM, and its TC was found to be 35 Kelvin. So these are copper-based materials, right, whose TC was 35 Kelvin, and which essentially revolutionized our understanding about superconductivity material. And of course, for this, Benrose and Muller got Nobel Prize in the year 1987. Right. Once this was discovered, so then there was also 1987, yttrium barium copper oxide was discovered, whose TC was 93 Kelvin. This was another breakthrough because now you have superconducting above liquid nitrogen temperature, right? So this is what another breakthrough, because previously Kamerlingh Owens discovered superconductivity, which was below liquid helium temperature. So now you could push the transition temperature to 93 Kelvin, which is above liquid nitrogen temperature. Well, so in 1988, materials was discovered, which was TC was 125 Kelvin. That was the highest TC which was possible. In between, right, between 1988 to 2018 or 2019, several materials have been discovered. But room temperature superconductivity. We'd like to have superconducting materials at 300 Kelvin. That, of course, remained a kind of, remained a kind of unfulfilled dream. Well, so the latest was in 1993. This was this mercury cuprate, whose TC turned out to be something like 133 Kelvin. Well, so this could be done. So this is what a superconductivity, the property that a superconductor satisfies is what? Number one is that it should have zero resistivity, right? If it has zero resistivity, then the current will essentially, if it's a superconductor, the current will essentially move on without any loss, right? So current can flow for about 100,000 years, right? So this is a compound which is superconducting at 77 Kelvin. Another interesting property which superconductors have, so a superconductor is a perfect diamagnet, right? It expels the flux, right? So this is one, and this is what is known as Meissner effect, right? So what happens here on the surface of a superconductor, when temperature is lower than Tc, superconducting current will be induced, and this creates a magnetic field compensating the outside one, right? And as a consequence, what you have, so you have a superconductor, right? And this is a magnetic element, and this magnetic element is essentially levitated, right? And this, of course, finds an important application, as I will show you, right? But one of the bottleneck had been that so all these properties are useful, provide a system superconducts at a higher temperature. Well, so the mechanism of superconductivity, right? Mechanism, not for the mechanism for the high temperature superconductor, mechanism for the usual superconductor was discovered by Bardeen, Cooper, and Schrieffer. And I also told you that Bardeen essentially got 2 Nobel Prize. The first Nobel Prize Bardeen got was because of the discovery of transistor. The second Nobel Prize which Bardeen got, which was because of the discovery of the theory of superconductivity, which is known as Bardeen-Cooper-Schrieffer theory, or the BCS theory, right? So electrons usually repel each other, but in superconductors, electrons attract each other. And how electrons attract each other is something which was essentially proposed by Bardeen, Cooper, and Schrieffer. And this attraction takes place by deformation of the lattice or deformation of the structure, right? Where the superconductor belongs to, and that essentially gives rise to an attractive interaction, and which eventually leads to superconducting property. And these electrons, which essentially superconducts, are known as Cooper pairs. Well, as I was trying to tell you, that the high temperature superconductor which yielded is this lanthanum copper oxide, and this is what the structure is. And this was the lanthanum copper oxide, and where the superconductivity essentially takes place in what are known as copper oxide planes, and it has this interesting phase diagram. The parent compound happens to be antiferromagnet, and these antiferromagnets are a different kind of a metal which cannot be explained by the band theory that I talked about. This requires a total new kind of concept like Mott insulators and so on and so forth, right? And this is something which you people may get interested at some stage and try to understand, right? And when you go ahead and start hole doping, then for this concentration of hole, right, about 1.15 hole doping, they become a superconductor with highest TC, and this is what is known as optimal doping. Well, still, as I told you, the superconductivity in high TC cuprates could be pushed to about 140 Kelvin, which is definitely far away from the dream. And what is this dream? The dream is to get a room temperature superconductor. Well, I will end this talk with an optimal note. In fact, this year, I think this is a very recent paper, I think maybe a couple of weeks back, there is essentially a report in Nature of the discovery of room temperature superconductivity in this hydrogen sulfide compound under extremely high pressure, right? This is what it is, that if you put this compound under extremely high pressure, it starts superconducting, and it starts superconducting at a temperature which is close to 300 Kelvin, which is close to room temperature. But of course, it is a pitfall that you have to essentially go ahead and lower the temperature to a point that so you have to essentially apply a pressure, and which is of course not a very easy thing to do. But the positive part of this entire story is that you have been able to discover a material which can superconduct at a temperature which is room temperature, and where one can find application. And the application which one has in mind is, of course, this levitating trains. Now, if we have a superconducting material which superconducts at room temperature, then railway tracks could be made by the superconducting, and this levitation could now be achieved by so-called Meissner effect or Meissner effect, and that will essentially make our communication or make our transportation easier, faster, and much more effective. Well, with this points, I'd like to end today, and I'll thank you all for your attention. And if you have any questions, comments, and things, I'll be very happy to take it up. So thank you very much for your attention. I guess I finished on time, and I think I have 5 minutes if people are interested.
Thank you, sir, for your wonderful session, sir. We have some questions. So if you allow, we can start our discussion session, sir. So we got one question in the private chat in our StreamYard. So in every nanomaterial in 1 to 100 nanometer range shows quantum effect. If the material shows quantum effect above 100 nanometer, then can we say it is nanomaterial?
For example, I of course did not disclose for example, the kind of properties that I have talked about. See, the thing is that since this talk is intended for youngsters, I did not go into much detail. So not every material will show this optical property, right? So for example, to show this particular kind of optical property, what you need to have is, so there is a scale, and this scale is called what is known as excitonic Bohr radius, right? When light falls on the system, it liberates electrons, and these liberated electrons forms what are known as holes, and this electron and hole, they essentially form a bound state which is called an exciton. When the dimension of this exciton is comparable to the dimension of system size, then only quantum effects are seen. This is what the entire thing is. So if you make this system size 100 nanometers, you may not see this quantum effect because this excitonic radius may no longer be comparable to the dimension of this thing, right? So to see this quantum effect, right, we have to make sure several other things to hold good, but the basic principle is nothing but that of a particle in a box. Okay.
Thank you, sir. We have another question. So why we need a quantum mechanics for the
right?
object?
So this is a interesting question. We need for the tiny object, as I was trying to tell you, quantum mechanics is at work because of a principle which is called Heisenberg's uncertainty principle, right? When you go to this microscopic domain, where this is what is this, that the object loses its particle-like entity. It has both particle-like and wave-like behavior, right? This is the wave function or wave-particle duality which sets in. And this only sets in when you go to this microscopic size. And this is where now you can, unlike your Newton's laws of motion, for example, if you take a cricket ball or if you take a football, its position and momentum can be specified at any point in space. But when you go to these tiny objects which are less than a nanometer, less than 10 to the -9 meter, right, you cannot specify its position and its momentum precisely at the same time. I would say precisely, and this is what is known as Heisenberg's uncertainty principle. And as a consequence, you cannot use Newton's equation of motion. Your interpretation changes. Your interpretation is no longer deterministic. Your interpretation is now probabilistic. You can only say probability of finding the particle at a certain point in space. You cannot say the particle will be there, right? And all this comes through by solving Schrodinger's equation, right, which gives you wave function and it gives you a probabilistic interpretation in terms of wave function. And of course, as I was trying to tell you, if this particle is confined, then the energy levels are no longer continuous. It becomes discrete, and then they start showing up properties that we started seeing in our nanoparticles.
Thank you, sir. So we have another question, sir. So what is antibond?
What is an antibond? Which is a very good question, right? So for example, which I was trying to tell that if you have two atoms, right? So if these two atoms are far away from each other, then they will not interact, right? But when you bring this, so they will have their own individual ground state, right? So so for example, let us consider two hydrogen atoms. Each hydrogen atom will have one electron each, right? So in the ground state, they will be occupying their private ground state. Now, if you bring these two hydrogen atoms together, then their wave functions will overlap. Once their wave functions will overlap, then the energy levels will change. It will create a bonding level and an anti-bonding level. This is something which I was trying to tell. It will create a bonding level. The bonding level lowers its energy. The wave function will not have any node. On the contrary, and which is essentially addition of these two wave functions, which will create a bonding level, and difference between the wave function will create an anti-bonding level, which will have a higher energy. So the anti-bonding state has a higher energy, and the two electrons available will occupy the bonding state, and the anti-bonding state will be empty. As a consequence, when you bring two hydrogen atoms to form a molecule, the energy is lower, forming a molecule, so hydrogen molecule is formed. This higher unoccupied energy level is called an anti-bonding state.
Thank you, sir. We have another question. So in which condition quantum mechanics reduces to classical mechanics?
Right. So this is what is a very important question. When h cut goes to 0, right? So this is what it is. That is what delta x delta p, right, is equal to some h cut by 2 or something. When that h cut goes to 0, then the uncertainty in position and uncertainty in momentum essentially goes to 0, and that essentially then classical mechanics reduces to quantum mechanics. Right.
Thank you, sir. We have another question, sir. So can you please explain my question that will helpful for me? How can understand complex of matter and biological system?
Right. So this is fine. So this depends on the kind of questions you are asking, right? For example, when you are talking about soft matter or biological systems, right? Often the size is so big, so size is of order of microns or even slightly more than micron, where your classical description holds good, right? When the size is, so for example, in many cases, in many biological systems, you can essentially model these systems by taking balls and springs and things like that, and using classical laws, right? So what I'm trying to say is that many questions for biological systems, of course, I'm not a biologist, or I won't be able to tell you, or what is known as soft condensed matter physics. The length scale is usually of the order of few microns, right? And there, for example, you can use classical mechanics and explain your things. But for example, if you want to understand a property of a protein, right, or dictate the property of a protein, then you may have to use quantum mechanics, because then you have to go to the atoms which constitutes the protein and eventually the electrons and so on and so forth. But this kind of calculation happens to be very ambitious, because these are very big systems, and to do a quantum mechanical simulation becomes difficult. But most questions for biological systems, right, can be addressed by using Newton's laws of motion.
Thank you, sir. We have another question. So, sir, can you explain the concept of resonating valence band theory?
Okay, so right. So now I'm coming to slightly more experts. Right. So this is concerning this high temperature superconductors. So it's a good question. So that it's good that somebody asked this question. And this resonating valence bond has become very fashionable in today's research. So the person who has asked this question, so let me tell you that you have asked a very pertinent question. So the parent, for example, let us take an example, lanthanum cuprate. So what is lanthanum cuprate? So La2CuO4. This La2CuO4 is an antiferromagnet, and it's not only an antiferromagnet, this is an insulator, and what is known as a Mott insulator. So when you take this system, this is definitely not a superconductor. That's what I was trying to show you in the phase diagram. But when you take this system and dope it with strontium, that means you are essentially producing holes, then what happens is long-range antiferromagnetism is lost. Then what happens, right? Then what happens is that these spins, right, they essentially form what are known as singlets, right? So what happens is, so there is no long-range antiferromagnetic order, but there is some short-range antiferromagnetic order, right? That means an upspin tries to pair up with a downspin, right? And which downspin it will take is essentially non-deterministic, right? And this pairing up of upspin with downspin, right, this is what is known as a resonating valence bond. And what is essentially thought that this resonating valence bond, right, essentially leads to superconductivity. This is one of the things which people have talked about. And this resonating valence bond, which do not have any long-range order, often is like a liquid, right? And so these are also often known as spin liquids. right? And people have been very much interested in spin liquid in today's world, because spin liquids, so every magnet has an excitations of spin liquids are what is known as Majorana fermions, and they are expected to find application in designing quantum computers. So you can see again quantum mechanics comes into picture, that if you can get a spin liquid, right? So the spin liquid's excitations are Majorana fermions. This is what the expectation is, and this Majorana fermions can find application in what are known as quantum computers. So these are valence bonds. So what are valence bonds? Valence bonds are random singlets, right, formed by this up spin and down spin, right, and they never order, right. So they are continuously changing their singlet partners, right, and giving rise to a kind of quantum fluctuation in the system, which is expected to cause pairing. That pairing that we talked about, Bardeen, Cooper, and Schiffer, is driven by the lattice distortion. But here, for example, for the high TC cuprates, this is not driven by the lattice distortion, but it is reflected by this so-called short-range magnetic interactions, and this is often quoted as spin fluctuation-induced superconductivity.
Well, thank you, sir. We have another question. So, how can the transactional interpretation can be applied to relativistic quantum mechanics?
So, I have not really understood the question. How can the
the word
so I have not understood the question, but let me try to give an answer. So, for example, of course, we have to use relativistic quantum mechanics, and the basis of relativistic quantum mechanics is Dirac equation, right? So, for example, so we write down. So the thing is that for example, when we are talking up, so for example, electrons, right? So real electrons are, in fact, principles are relativistic particles. So what we do is essentially we have to incorporate the effect of relativity, and what one does, for example, there are a variety of ways to go ahead and do relativity. One of the easiest way to do is Klein-Gordon equation, but Klein-Gordon equation has its own problem. But linearized version of Klein-Gordon equation is Dirac equation, and Dirac equation is routinely used to understand quantum mechanics or relativistic quantum mechanics, right? So this is routinely used if you're interested in high energy physics, right? When the energy of the system is higher, right? So then, of course, we have to go ahead and use, we have to abandon Schrodinger's picture, which is non-relativistic. We have to bring in Einstein's relativity in quantum mechanics, and this is what is known as your relativistic quantum mechanics.
So thank you, sir. We have another question, sir. So what's the impact of quantum materials on electronic accessories? So can you please explain?
So as I was trying to tell you that so for example, we are all very happy with the silicon industry, right? And we could see that every 10 years the size of the device was shrinking, because what you could do, you can pack in thousands and billions of ICs in a small chip. But then it came, so that then automatically there is a limitation. You cannot do that, because if you start reducing the size, right? So for example, the typical systems that we use, right? These are known as microelectronics. The chip size is of the order of few microns, where your classical description starts holding, right? But now if you want to make the chip size smaller, that if you want to make the miniaturization, then what you have to do, you have to go to the nano size limit, 10 to the power 9 meter, then all your quantum effects will start coming in, right? So you have to have a quantum device, right? And how to handle this quantum device is something which is not quite clear. And this is where, for example, came in the idea of utilizing the idea of using electron spins, right? So and electron spin is totally a quantum effect, and this is something which was first used to show you the GMR effect, right? That's which I was trying to explain you. I don't know whether I could get the things through, but this GMR was the first example where the electron spin was used for the purpose of storage, for the purpose of switching, so on and so forth, right? So this is where the quantum effects are coming in, and eventually people are now taking a transition from microelectronics to nanoelectronics, right? So people are trying to do that, and again, there are a lot of research going on how you can really design a quantum device, right? And eventual aim is, of course, to have a quantum computer. right, which will be highly sophisticated and highly efficient in doing all our day-to-day job, right? Of course, if these all are in a research level, and these are something which are very exciting areas, and some of you who are young, right, should definitely take up this aspect of physics, which is so-called quantum condensed matter physics.
Thank you, sir. We have another question. So why hydrogen atoms ground state wave function is spherically symmetric?
Why hydrogen atoms ground state wave function is spherically symmetric, right? So this you can see because it is 1s orbital, and the thing is that, as I was trying to tell you, that I mean, one of the very simplest way to understand this would be that the less number of nodes, right? If there are less number of nodes in the system, right, then the energy is lower, right? And you can see, if you think of a spherically symmetric wave function, it hardly has any nodes except at the two endpoints, right? Which essentially tells us that the ground state wave function, if it adopts a spherical symmetry, right, it will have a lower energy, and this is precisely the reason why your ground state wave function for a hydrogen atom is spherically symmetric.
Thank you, sir. This may be the last question.
Yeah.
About discussion. Sir, you mentioned about the spin liquids and Majorana fermions. So in quantum spin liquids, there comes a concept called fractional quantum mechanics. How much valid?
No, so it is not fractional quantum mechanics. So for example, so don't confuse. What essentially comes up is that the excitation. So for example, so this is I have to talk a little bit advanced in this. So this is not fractional. So excitations are fractional, right? So quantum mechanics cannot be fractional, right? So the quantum excitations are fractional. So what do we mean by that? So for example, if you have a ferromagnet, and so where all spins are up, if you flip one spin, right, then the excited state will have one up and one down spin. So this will essentially create a bosonic excitation. So for example, once you have a spin liquid, the excitations are no longer bosonic, so they are fractional, right? This is what it is. So they are fractional, and this is where, and as a consequence, these excitations are Majorana fermions, so on and so forth, right? So this is where it comes up. So these are no longer usual magnons or bosonic excitations; they are fractional, and that's from where this fractional excitations comes in, right? It's not fractional quantum mechanics.
Thank you, sir, for your wonderful lecture and exciting discussion sessions. I think students have learned a lot of things from your lecture and this discussion session. So we should conclude this discussion session, as there is no more question in our discussion session. So thanks again, sir, for accepting our invitation. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. So I will definitely invite you for a face-to-face session in our university after the COVID. So thanks again, sir, for wonderful presentation, sir.
Okay, thank you so much, Professor Das. It was really wonderful in participating, and well, I don't know how much it was understandable, but well, I mean, I think I could share some of the excitements in this field, and thank you for giving an opportunity to interact with students of your university and, of course, many other people. And I also thank all the audience and your department, and definitely you. So thank you so much.
It's my pleasure, sir. It's my honor and privilege, actually, sir, to host you in my international physics webinar. Thanks again, sir. Good night, sir.
Thank you so much.
Bye for today, and see you very soon, sir.
We shall be in touch, definitely.
Yeah.